We're going to be looking at another variation of dealing with means and hypothesis tests, and this one's going to involve two different samples. So our setup here, our question is that there's a statistician who believes that physical contact would shorten your career in pro sports. So based on that, you would believe that pro baseball players would be older than pro football players on average. So what she does is she selects one person or one player at random from each team, and the results are below here. Uh, you don't have all the data, but you are told the histogram of each data set would be roughly unimodal and symmetric. And the question is there evidence that MLB players are older than NFL players? So what we're going to say here is, first of all, in terms of our null, is that there would be no difference between them. And that means if we took the mean age of all the MLB players and subtract out all the mean age of the NFL players, it would be 0. By the way, in case it's not obvious by now, I'm using 1 and 2. So what you want to do is you want to define who's 1 and who's 2, and it kind of depends on how you feel like doing it. I'm going to say 1 is MLB and 2 would be NFL, and then also define mu. So that would be the age. All right, and then in terms of our alternate hypothesis, we would do the same thing, mu1 minus mu2. And if it is indeed that baseball players are older, we would take a bigger number minus a smaller number, and that would give us a positive number. So we're going to say greater than 0. So this number 0 is really key here because this is going to be our mu later when we actually would do our hypothesis test. All right, let's move on to conditions now. There's 4 of them. Number 1, are the samples independent of each other? So in other words, does the age of an NFL player affect those ages in Major League Baseball and vice versa? I mean, no, they're just totally independent of each other. They don't affect each other at all. Both sample sizes would be less than 10% of all players. So 30 is less than 10% of all baseball players. Likewise for football players over here. It says the players were randomly chosen. So there's your random that you need to see showing up in your question. As always, it would be nice to see the actual data and make a histogram. Uh, we didn't have that, but what's nice though is our sample sizes are a little kind of on the border here. One's at 30, one's at 32. But what does it say in the problem? It says, going back here, it says that it would be roughly unimodal and symmetric if we made a histogram. So therefore, you can say they would be approximately normal because that's what symmetric and unimodal looks like. And our test, we call it a two-sample t-test because we're comparing one sample versus another sample. So in terms of the work here, I just rewrote everything we were given earlier, the means, the standard deviations, the ends. I also found the difference between x bar the first and x bar the second, and that ended up being a difference here of about 1.2. Degrees of freedom is a little different. There is no formula really for this. I mean, there is, but it's super complicated. So you can't just say 30 plus 32 is 62 and subtract 1 or 2. Clearly, this isn't that. You're going to get it from the graphing calculator. So what you want to do is do stat and test and go to 4 2-sam t-test. And if you input all the numbers in their stats and just run it, you'll be told what this degrees of freedom is. So it's 50.95. So let's go ahead right now and actually do the math. So I'm going to go ahead and draw my t-curve. It's a t-curve with 50.95 degrees of freedom. Our mu is going to be 0 because we're assuming that there is no difference between the groups. How we find the standard error? There is a formula for this. And that formula would be, draw a big square root, and there's going to be two fractions there. One of them would be, I'm going to do this for baseball first, that was the actual sample size. Its standard deviation was 4.17, and you square it. For football, the standard deviation was 2.86. You're going to square that and then put this sample size or n on the bottom. So when you run this in your calculator, you should get a standard error of about 0.914. So that's going to be the variability that we're going to be using here when we actually do our t-score. So our t-score will be, oops, you know what I forgot to do over here on the curve? I need to put in the difference between these two. So 1.2 is going to go over here. So that is x bar 1 minus x bar 2. All right, back to the t-score here. So we are going to take 1.2, subtract 0, and divide by 0.914. So when I did that, I got a t-value of about 1.313. And then what you're going to do is you're going to find your p-value. So it's going to be p-value is the probability that of t 50.95 being greater than 1.313. When you do this on the calculator, remember what you're doing is you're doing t CDF, and that's going to be 1.313 comma 99, and then we have degrees of freedom of about 50.95. All right, when you do that, you will get a p-value of 0.098 or thereabouts. And as you guys know by now, if we're below 5%, we reject, but we aren't. So we're above 5%, so we are going to fail to reject the null hypothesis since p is greater than 5%. There is insufficient evidence that Major League Baseball players are older than NFL players. So were they older on average? Sure, but just not enough for us to lead. It just could have been sampling variability in this case here. All right, in terms of our confidence interval, we're going to take over here, we're going to take the difference in our two means, which we already knew to be 1.2. Our standard error we know from that problem was already 0.914. We're going to use t star 50.95. So remember, to do that, you're going to do inverse t, and you're going to use 0.95, and that comes from 90 plus half of the remaining 10. Half of 10 is 5, 90 plus 5 is 95, and then it's 50.95 right over here. So when I did that on the calculator, I got 1.675. Let's go ahead and multiply these two together to get our margin of error. So when I multiply these two together, I got a margin of error of about 1.53. And if I take 1.2 and add and subtract that margin of error, I get on the low end, I get a negative number. And on the high end, I get a positive number, which I'm not surprised because if you fail to reject, 0, which is our null hypothesis, should be in here, and it is. So we have negative on one end, positive on the other, so 0 definitely is in the middle there. So when this happens, your statement will look a little funky. So we're going to say we are 90% confident. And remember, this is about a difference between them. So we're going to say that MLB players on average, let's just say average, 0.33 fewer to, and on the high end, this would be more. So 2.73 more years of age than NFL players. So it looks like, based on what we came up with, on average, they might actually be a little younger than NFL players, that much less, or they might be that much older, somewhere in that range right there. So there you have it, a two-sample t-test, and this is called a two-sample t interval.